All right, thanks. Well, I'm really glad to be here. I was going to apologize for my attire, but I see that I don't need to because I'm not the only one here wearing a hoodie and a hat and boots. I knew we were going to the woods, and I knew it was going to be cold, so I feel like I'm with my people. I am a scientist. I've been with the Southern Station for about 25 years now. Southern Research Station, which is headquartered in Asheville, but our lab is in Athens, and I am part of the Climate Hub, but I'm also part of this group, the Athens Prescribed Fire Lab, which is headed up by Joe O'Brien, and we've got lots of great folks there, including some colleagues at UGA who are major collaborators. And I'm going to talk to you today about some of the work from there and really from the beginning of my career. So if we go back to the very beginning of my career, when I was about 9 years old, I was responsible for a wildfire. Which I'm not proud of, but we were playing with matches and started a wildfire. And then again, before I was 13, was responsible for another wildfire. Both of these were limited in extent, right? But my dad said, you guys can't go do that until you empty the firebox out of ashes. And so we dumped hot ashes down the hill and lit a stand of Virginia pine on fire. I grew up in North Georgia at the very end of that Blue Ridge Escarpment in Dahlonega. If you all know where Dahlonega is by any chance. My dad was a biology teacher, Matt Callham Sr. at North Georgia College at the time. And so the apple didn't fall very far from the tree. We both went to UGA. My sister went to UGA. My kids are going to UGA. So I'm a Georgia guy. And so you have to take that or leave it. All right. So I started my Forest Service career as a postdoc working with a guy named Tom Waldrop, who was in cahoots with a guy named Dean Simon, and they started this big study called the Fire and Fire Surrogate Study at the Green River Game Lands. And I was a postdoc, and that was my first job. And so it's really, it feels like a full circle kind of moment here. And I'm so glad that that site is still a viable demonstration site, still a viable experimental site. We've got people working on their graduate degrees now on that site. And so it's so gratifying to me to have been involved in a long-term study. And I hope it'll be worthwhile for y'all to go out there and take a look at what we've been doing. So I can't go any further without talking about my colleagues, the major contributors. You might call them co-authors if you were an academic. So Melanie Taylor is responsible for a great proportion of the work that's going to be presented today. And she was a Forest Service employee until April or May, U.S. Forest Service employee, and she was simultaneously working on her PhD at University of Georgia. So she's now in a postdoc position at NC State. Go Pack, I guess. Don Hagen at Clemson. Nina Wurzburger is a UGA colleague. She's a microbiologist, soil microbiologist, biogeochemist, totally amazing intellect. Joe O'Brien, as I've already mentioned, Louise Loudermilk and Dexter Strother are my colleagues at the Athens Fire Lab. There's others, but these guys are the ones who really deserve equal credit. I'm just here as a mouthpiece, except I've been here the whole time. Okay, so I like to just kind of check in with everybody. I hope this will be a conversation. I hate standing here and droning on and on. So if I say something that doesn't make sense or that you want clarification on, or that you want to disagree with, pipe up, because otherwise it's going to get long and boring. So I'm just going to talk a little bit about the history of fire in North America, probably preaching to the choir, but I love talking about it, so you're just going to have to deal with that. Then talk a little bit about where we are now. We've already heard some of this from our previous speakers. And then probably the meat of the talk will be results from current studies and maybe you could call it a past study at this point. So fire is an extremely important factor, right? We know it's been shaping ecosystems in North America and probably all over the world for 430 million years, right? We've got fossil charcoal from 430 million years ago, which is coincident with oxygen levels in the atmosphere reaching a level that combustion can be sustained, right? That happened 430 million years ago, and there's been fire happening on Earth ever since. We all know about the influences that can happen on vegetation. We talk about elemental dynamics, the flow of nutrients, fluxes of carbon, and so on and so forth. We know fire interacts with climate, and there's a long human history, and I'm going to talk about that. I'm not an expert, but I do find that a fascinating subject. And there's evidence to support all of this, and I'm just going to hit some of the high points. So how many of you have seen this figure before? Okay, a few of you, maybe 40%. So this is from Rich Guyette's group at the University of Missouri. A lot of people say that this is a return interval, but it's not return interval. What this is a model of the potential return interval of the vegetation. So what they did is they took sorry, easy for me to say. The chemical composition of the vegetation, the climate of the area, um, the structure of that vegetation, and they put it all into a big model. And so they predict that the vegetation based on these characteristics can burn at that frequency that's indicated. So sort of the physical basis of what will and when it will burn. So there are places where the potential and the actual incidence of fire are the same, which is cool, right? But it's only on a small portion of the landscape anymore. And you can see that in the southeast, that it's pretty frequent. The vegetation essentially wants to be on fire. It's adapted for that. Then we can look at even a sort of a historic record here. This is from a paper by Sally Horn at University of Tennessee. I'm not going to say go that team. So, all right, we got one. So this goes back 24,000 years ago, and what they did is they sampled sediment from the bottom of a pond called Anderson Pond, which is kind of in north central Tennessee. I think it's in White County. Does it say there? I think it's in White County, Tennessee, which is north central. And so this is an amazing record. It's of pollen and dust and charcoal and stuff that has been deposited in that sediment for 24,000 years. And we know it's that old because they've got radiocarbon dating to substantiate that, right? And so if you look, about 24,000 years ago, a big part of the continent was covered in ice, right? All the way down to sort of southern Ohio. So not far from where this is, frankly. And so you can look at the vegetation mix and you can see that pines were very well represented up until about 13,000 years ago, at least. And if you look for things like oaks, they're in there, but they're kind of piddling along until about the same time the pines drop out, right? And what species of pine this is anybody's guess. Probably not loblolly or longleaf or slash, right? Just we're probably looking at jack pine and red pine and things that are living in Canada now, right? Okay, and then the other mix, the other things are similarly dynamic, right? So about 8,000 years ago, there's a little bit of a hiatus in the record, which is why that is blank all the way through. But about 7,000 years ago, there's a big spike in charcoal. So it's coincident with the change in vegetation, but it's also coincident with what? The radiation of human beings onto the continent, right? This is maybe even lagging that event itself. But we know that people were widespread in the Southeast 8,000 years ago. We know that people were using fire, as has already been alluded to in Adam's talk, I think. And so what I think is quite interesting is that about 14,000 years ago, what else happened? The glaciers started to retreat northward. So human beings moved in as soon as the glaciers retreated, and this massive reorganization of the vegetation happened simultaneously. And so we would argue that human beings have been, through their use of fire, deciding what the vegetation community is going to be. Maybe not deciding per se, but at least influencing what the vegetation is going to be since the glaciers made it possible. The glacial retreat made it possible. So you can't extract humanity from the process of vegetation dynamics and community composition. That's cool, right? That's what we're all about in this room, is trying to influence that. And so there's a tradition that dates back a long time, longer than a lot of people think. All right, so more evidence that human beings were using fire. How many of you guys know about John Lawson? He was the first English-speaking one of the first English-speaking explorers in the Carolinas, and he did this big voyage where he put in at Charleston, paddled canoes with guides, some of whom were native, um, up into the Piedmont and then across the Piedmont, and then came out around, I guess, Wilmington somewhere. So they didn't quite get to the mountains, but they could see the mountains from where they were based on what you can read in the diary. And so in his diary, he wrote in January, so not growing season, I think that's important. January of 1701, he wrote, "We traveled 20 miles lying near a savanna that was overflown with water," so they're probably in the coastal plain still, "where we were very short of victuals, but finding the woods newly burnt and on fire in many places, which gave us great hope that Indians were not far off." So there's a lot to unpack there as far as I'm concerned. One, the native people were using cultural burning practices in the winter, the dead of winter, to achieve their goals, whatever they were, right? So all the talk about it has to be growing season fire, I think, is misguided because we know that people have been using fire every month of the calendar for as long as they've been there, right? Okay, the second thing is he expected to get help from the natives. That gave them hope that they were going to get their short victuals fixed. And the reason, Lawson's journals, the reason why we know about him mainly is because he did document his interactions with the native people. The natural history in the journals is not that great, frankly, from my perspective. He was no William Bartram. But all that is detailed in this great book by another NC Stater, Scott Hewler, which is called A Delicious Country, Rediscovering the Carolinas Along the Route of John Lawson's 1700 Expedition. I recommend that book. I don't recommend Lawson's because it's pretty dry. Anyway, if y'all are interested in that kind of history, it's worth a read. All right. And I'm not going to spoil it for you and tell you how John Lawson's deal ended. You have to find that out yourself. Uh-oh. That's Lawson's term. He called it a delicious country. This thing is hung up. Sarah, help me. Oh, here we go. All right. So one point that I want to make is that I think that tradition of burning the woods, human use of fire, is maintained in the Southeast. If you look at the number, this is old data from 2018, but if you look at the number of acres burned in prescribed fires on that side versus the number of acres burned in wildfires on this side, you can see that Georgia, Alabama, and Florida combine to burn as many acres on purpose as they burn by accident in the West, right? Which I think there's a direct link to the indigenous person's use of fire and their interactions with the early colonists, right? Where there was still this possibility of learning from each other that persists in our management of our ecosystems here today. Yes? No? Maybe a tenuous connection, but I think it's there. All right. So I'm going to move into I'm a soil scientist. I should have said that at the beginning. I was trained in agronomy. I got a master's degree in agronomy from UGA back in the, I don't know, late 20th century, as the kids say these days. And so, everything I say and the way I look at the world has to be passed through this filter of soils. And so again, you guys just have to bear with me on this. But I think if you're going to be a fire ecologist and you're going to be a soil scientist at the same time, then the crux of the matter is going to be played out in this O horizon. So in soil taxonomy, that what you guys are calling Duff, litter and Duff, is what a soil scientist would call the O horizon. Everybody had a soils class? Most people had a soils class? So again, this is review for you then. So O horizon is broken out in the soil science literature in OI, OE, and OA, and they differ in that this is brand new litter, this is partially decomposed litter or slightly fragmented litter. You can still look at it and see that there's parts of leaves and stems and things in there. But when you get down into the OA, And that's properly called Duff, right? And in my mind, when I take a field crew out and I say, we're sampling Duff, they say, what's that? Is this Duff? And so I tell them to apply a mental leaf blower. And so when you apply that mental leaf blower, everything that can get moved by a leaf blower is litter. Everything that's stuck together by fungal mycelia or roots or whatever else, that's appropriately called Duff. Maybe some of you fire managers would disagree with me. I'd like to know what you think about that. Um, and then, so when you get into the OA, that's the very highly decomposed material. Some people call it humus. In the European system, it's L, F, and H for litter, fermentation, and humus layers, but they are functionally the same. And so what we call Duff, what foresters call Duff, is that part right there. And so, right, the name of this workshop is Duff in the Mountains. So I probably didn't have to explain that, but I'm giving it to you from the soil scientist perspective. All right, so why do we care about that? Soil, probably the most important natural resource. I say this again through this filter. It's important. It's up there with water and air, I think, right? As far as like sustaining resources go. We could debate the details of that, I guess. But one thing that is often lost about soil is that it's really dynamic. It's a dynamic reactor of mineral and organic and, well, animal, plant, and organic particles, and water and air. Like there's a lot going on, and it's responsive to disturbances. So we know that if we set a fire in a place, the soil is going to respond one way that's different from what it would be if it was left unburned. Same thing with other disturbances like grazing or, I don't know, pick your disturbance. Soil does respond. And for me, I'm, pretty much of a nerd, I guess I would say. I think about it in terms of this reservoir of biological diversity, both microbial and microscopic animals and macroscopic animals, just unbelievable. I could spend the rest of my life, have already spent like 30 years digging holes. And I think I could probably spend the rest of my life digging more holes. My back holds up. Okay, so enter Melanie Taylor. She, as I said, used to work for us in the fire lab and is now a postdoc at NC State. Around the time she started working for us, there was this outbreak of wildfires in 2016. And so she was really interested in trying to develop a project and work alongside others who were working on this project, looking at the effects of this fire, which was the Rock Mountain Fire in North Georgia. Some of y'all maybe were on that fire, I don't know. But it even kind of slopped over into the Nantahala, right across the Georgia border near Tate City, Georgia, west of Clayton. So flash droughts, fall of 2016, the fire ignited on November 22nd. This is what the US drought monitor looked like. So you can see we had a serious drought. It hadn't rained, in Athens, it hadn't rained a drop in about 100 days by this time. So my friend and colleague, Steve Norman, who lives and works here in Asheville, is just up that way, I guess. I love this presentation of data. So he's looking at the fall weather conditions for the last year. Well, it stops in 2016, from 1970 to 2016. And so the decade or the year bins, I guess they're 15-year bins, are the different colors. And then that's dry to wet, and this is cold to hot. And dry to wet is average regional stream flow, is what he used as a proxy for dry to wet. So he arrays all the years out on that matrix, that grid there, and you don't really see much in terms of like a temporal trend, except that 2016 was the hottest and the driest on record. So keep your eye on 2016. The rest of them are pretty interesting too. And so, this line, the 1-to-1 line, is kind of what we think might be like average conditions, although it really goes more like that. So this is the size of the balloon now is equivalent to the number of fires that happened that year. Maybe the balloons are slightly larger. Maybe there's slightly more fires, on the, hot and wet or hot and dry side of the thing than there are down there. But really, again, not much of a pattern. And 2016 is unremarkable with regard to the number of fires. But then, so everybody grab the table, get steady. This is the area burned in those fires. And I mean, seems pretty obvious, right? That looks like the Death Star, 2016. And there are people here who would talk to me about, well, there were a lot of decisions about how we were going to fight those fires when they started, and that's true. It was an intentional strategy to let them burn out in places where we could. So they got bigger somewhat on purpose, but there still is this strong relationship between hot and dry conditions and the size of fires, the acres we can expect to get burned. And I don't have to tell you that the prediction is for hotter and drier conditions in the future. Okay, so Rock Mountain, let's go back to Rock Mountain. This is a fire severity map produced in a Bear burned area emergency response exercise following the wildfire. You can see that most of it was very low fire severity, or at least modeled to have been very low fire severity, with ridge tops, as you might expect, being predominated by moderate and high severity. So what we did is we set up these plots. Each green star represents a plot, and some of them are inside the boundary of the fire, some of them are outside the boundary of the fire. And importantly, we arranged these so that the composition of the plots would range from like 0 or as close to 0% oak cover as we could, oak and hickory cover, to 100% oak and hickory cover. And this is going to get to some questions that we had about mesification and fire behavior and fire effects with relationship to the overstory canopy composition. So the reason for doing that gradient is because we know that mesification is happening, and we wanted to know what the effects were relative to the state of mesification that had happened in those plots. Everybody got mesification like in their lexicon? We all know what we're talking about, more or less. So you got your fire tolerant, we call them fire promoters, trees like oaks and hickories and used to be chestnut. They all have recalcitrant litter, which is a fancy word for saying that it decomposes slowly, right? It's got a lot more carbon per unit nitrogen in it, more flammable. Interestingly, this kind of litter is produced by trees that associate with ectomycorrhizal fungi. Everybody know what mycorrhizae are? Yeah, 2 different kinds of mycorrhizae, really 3 different kinds of mycorrhizae. The ectomycorrhizae are the ones that associate with these trees that we consider to be fire tolerant, fire promoters. When you don't burn them for 80 years or 100 years, you get a buildup of litter and duff underneath those because of the above mentioned factors. Usually the nutrient levels in those soils are low. Usually the litter is slow to decompose because of that. And you end up getting a major duff accumulation. On the other hand, fire intolerant species, fire inhibitors, you might call them, things like maple, acer, sweet gum is another one, liriodendron, poplar, tulip tree, whatever. They have what we would call labile litter, which is that it decomposes quickly. The soil invertebrates that live in these soils love poplar litter, right? And maple litter because it's delicious, apparently. And so the litter is less flammable. There's reasons for that. Like when an oak leaf gets wet, when it dries out, the edges of it curl up, right? And that produces a fluffy, well-aerated litter bed. What happens when poplar leaves get wet? They just kind of flatten out and they almost laminate, right? They'll almost form like leaves in a book. And so not well aerated, it doesn't carry fire well. All y'all know this from watching it on the ground, right? And interestingly, because of the rapid decomposition, we don't see as much duff accumulation in stands that are dominated by those trees. Those are AM mycorrhizal associates. are buscular mycorrhizae. And we could go, if Melanie was here, she could really give you a lesson on the differences between the biology and nutrient acquisition strategies and all that stuff about the mycorrhizae. But for now, we're just going to go with this. I have no idea how I'm doing on time. Pretty okay? I got another half hour, 15 minutes. Okay, so I drew this cartoon and I have showed it to a bunch of people. How many of y'all have seen me talk before? Some of you I know for sure. Armin's about to chew his arm off to get out of here. um, so this cartoon kind of, I try to make it as simple as possible in presentation. And so we're looking on this side, this is oak hickory fire suppressed condition, okay? So I already told you about the accumulation of duff. What I didn't talk to you about is the proliferation of fine roots in that duff layer. So the trees are not stupid. They know where the water and where the nutrients are in these ecosystems. I told you they're nutrient poor already, right? So if all the nutrients and water is tied up in the duff, they're going to put their roots there. But this is an unnatural state, right? The duff is an unnatural entity in these systems, but they're taking advantage of it. So what happens when that burns in a wildfire? It's dry enough, the duff burns. As Jonathan was talking about earlier, what happens to those roots? They're either burned up or they're left high and dry. They're not functioning as roots anymore, right? This is a pretty significant physiological hit for those trees, and we get delayed mortality. 3 years, 4 years, 5 years later, the tree looks great the next year, leaves out, everything's fine, doesn't know it's dead yet. Kind of like me. And then 5 years later, they're just like, I can't recover, you know. However, in a situation where you've got poplar and maple, fire suppressed, doesn't matter because we don't have duff forming. If you don't have a duff layer, you don't have roots that are exposed to the risk. You get a wildfire through there, maybe the litter's dry enough to burn, and we see that 100% litter consumption in those, fuel consumption in those stands, surface fuels, but there's no root mortality, so the trees do fine after the fire. We don't see delayed mortality in those poplars and maples, which is a little counterintuitive because I thought they were fire sensitive, right? So anyway, this is the essential. Cartoons are great. Conceptual models, fine, but what do the data show? Okay, so we've already seen pictures that look like this. This is the raging, devastating wildfire at Rock Mountain. You know, literally 8-inch flame height. Weenie, Joe O'Brien would call it a weenie little fire, right? But what you can't see because you're not looking at it carefully enough, if you look right here, you can see that there's an actual drop off down to the surface of the mineral soil behind this flaming front, where the duff has been totally and completely consumed. We're down to mineral soil there, along with all the roots and everything that went with it, right? So it doesn't look bad, but it is bad. And so this is, I've started calling this forest gingivitis, right? Because the gums or the roots are exposed, right? So there used to be duff right there. That's like, 15, 20 centimeters worth of duff that's no longer there. And you can just see these roots are exposed. There's all kinds of, what's the agent of mortality for these trees post-fire? Could just be that their roots are exposed and now they're more exposed to diseases or physical damage or whatever else it is. They've survived the fire fine, but later they're going to die. So we don't know if it's the big roots or the fine roots. Money's on the fine roots. But when you lose a bunch of roots, it's not good for the rest of the tree, right? And so this is another picture that is a mini scale version of what we were talking about, where you can see like this is the original surface and then it just drops off. And so a lot of times it burned out around a tree and then would send a little finger off until it got to an accumulation around a second tree or whatever, and then it would consume all around that tree. It's a really interesting fire behavior and fire movement phenomenon there. And these pictures are from the Chimney Tops 2 fire, which was in the Smokies. Okay, so back to the data. This is from a paper that was published by Dana Carpenter, who was one of Nina Wurzburger's students. And this is 2020. And so, this is, I joke around a little bit. This is suitable for publication in the International Journal of Duh, right? If you burn it, there's less of it left behind, right? And so the red is the line for the burned plots. This is the depth of average depth of the O horizon. And the blue is from our unburned plots. And yes, there's more left behind in the unburned plots than in the burned plots. But it's more complicated. Who was it who was saying it's complicated earlier? Yeah. So I used to go to these nerd meetings, the Ecological Society of America, and we would hand out like these bingo cards, and it had phrases like, it's complicated, or it's scale dependent, or it depends, And so every time somebody would say that during their talk, you'd get a chit on your thing. And occasionally some redneck from North Georgia would shout, bingo! Okay, so what happened above ground? Sorry, this is turning into a stand-up routine. So what does wildfire do to tree canopy is a question that foresters want to know, right? What's this doing to my resource? And so this is a little bit hard to interpret. What we're looking at is crown remaining. The lines represent crown remaining, and the yellow line, which is the one that moves the most, is the 76% or more of crown remaining. Okay, this is in 2019, so 3 years after the fire. And importantly, this axis is the amount of trees that were ECM or AM fungal associates. So 0% ECM means it's a tulip poplar maple stand. 100% means that it's an oak hickory stand. Is that clear? So when you go from this end, which is maple, almost 100% had 76% or more crown remaining. If you go over here to the oak hickory side, only about, 35, 40% had 76% crown remaining or more. And naturally, we see an increase in the other categories. So what it means is 3 years after, the crown condition in oak hickory stands on Rock Mountain was pitiful. And all of y'all have probably seen that from your respective fires as well, where you got a lot of duff consumption. It's important to look at the unburned side too. So we see that 76% or more crown condition actually increases on the oak side, right? So we are getting crown development in oak stands, crown fill in oak stands, as long as they're unburned. But what do we all know about fire? It's inevitable. Okay. Any questions? Everybody can give me an up and down nod. Okay. So for the Rock Mountain stuff, tree mortality, canopy decline predicted by species identity, specifically which mycorrhizal associate you had, right? I've already said this, surprisingly, the mesophytes, what we think of as the mesophytes, the fire intolerant species, were the ones that were less susceptible to wildfire damage than the fire tolerant ones. And of course, here's another one that was on the bingo card. There's more work to do. If you ever see like an ecologist or a biologist give a talk and they don't say, we have more work to do, they're charlatans. All right, so let's move on to the fire and fire surrogate study, which is what we're here to talk about today. 5 minutes? Okay. So the design of the experiment, y'all are all familiar, I hope, with the fact that we had control plots where there was no management done. Then we had mechanical treatment where understory shrubs were removed. We had fire only. That's been repeated 5 times now. The slide's a little old. And then the combination of prescribed fire and mechanical treatment. And importantly, Dean can tell us more maybe later about what the prescription was, because it was a little bit of a hot prescription, because the intent was really to reduce basal area in the canopy, or reduce canopy through reduction in basal area by burning a pretty hot fire. And so that's what these ended up looking like, which is kind of a little bit more of that woodlands look that we're going for, right? Where we had the mechanical and fire. Boy, I got to hurry. Okay. So recently, Melanie took all the data that was existing. We did a reanalysis of the original data that Tom Waldrop and his crew have been working on for 15 years or so. And we wanted to look at it through the specific lens of mesification and Duff, because that had not been a focus of the study per se earlier. So our principal metric was just change from 2001, which was my first year on the study, uh, to the last data that were collected by Don Hagen and his crew, including some Forest Service folks. So just change in whatever the metric was. And Melanie just got this paper out last year, it was in December of last year, in Ecological Applications, which is a big achievement. Okay, so what do we do to basal area? Everybody knows basal area, you're all foresters. This is in meters, but I gave a little guide there. So 8 square meters of BA is 86 square feet or so. So what was the change in basal area for our 3 treatments? You can see that the control treatment did nothing, not surprising. In fact, there was a little bit of an increase from 0, which, incremental growth. But mechanical treatment did nothing to reduce basal area. The fire treatment alone started to drop the basal area numbers a little bit. But when you do mechanical and fire is when you really get a significant drop in basal area, which you could have seen from those pictures if I'd left them up there long enough. Okay, so what does that mean? So we want to look at recruitment. We're interested in what the future forest is going to look like at Green River. So this is recruitment into the canopy class, so greater than 4 inches diameter. Control treatment, we actually had some recruitment into the canopy. The other treatments resulted in less recruitment to the canopy. So I guess that's okay, and that we're not creating at least more shade with those treatments. Okay, and mortality of the overstory trees, you can see that we had a really significant, pretty strong effect on overstory mortality in the mechanical plus fire treatment, which is what the target was, right, Dean? Okay, so what does repeated prescribed fire do to Duff at Green River? And this is, to me, a really interesting plot, even though it didn't make the final cut of the publication. We saw reductions in Duff with fire alone and dramatic reductions with mechanical and fire. So the question is, why does mechanical treatment reduce the Duff? And so this could get into some of these questions that we've had about Helene, which I think we should discuss later because I don't have a lot of time. But I think that when you get more light onto the surface of the soil, it's warmer, decomposition proceeds faster. And it's not like there were machines running over this place. These were hand-felling crews that did the mechanical treatment. So there's something about sunlight. It might be photodegradation. It might be warmer temperature, but there's something about it that makes that Duff decompose faster, which is interesting. Okay. And what does it do? What's the future forest look like in terms of species composition? So this is the number of saplings. When we had reduced basal area, the most dramatically reduced basal area was associated with an increase in the number of saplings per hectare. And then we can break it down into Acer, the brown ones, and Quercus, the kind of, what color is that? Teal. So the teal line actually goes up with greater reduction in basal area. So we're favoring the oaks, which is the stated goal, is try to get oak regeneration to happen. And then you can break it down by oak species, and you can see that white oak is actually the most, maybe it's, can't tell which is which, a little colorblind. Anyway, we're getting responses for all 4 of the important, sort of commercial oak species. And so we think that's good. And I'm going to skip this one in the interest of time. So repeated prescribed fires, effective at reducing Duff, thumbs up. Return interval on the order of 5 years for the fire. But I want to point out, like, it took us 100 years to get into the situation that we're in with Duff right now, and it might take 80 years to get out of it, because there's only so much you can do with a fire without damaging the overstory resource, right? So it could possibly be reduced with more frequent fires that don't consume Duff, but starve the Duff of the source material. So I've started talking about Duff as like being a monster, right? That it has to be fed to be maintained. And the food sources are litter, leaf litter, and roots. right? So when the roots grow in there, when they die, they're adding more to the duff also, right? So what the only strategy is for starving it is to just burn off the new litter every year, and that cuts out half of the source material for duff formation. And there's just, it will eventually disappear with enough time and enough reduction in that food source or feedstock or however you want to call it. So more frequent fires, as often as you can burn it, the better it is in terms of getting rid of duff, right? Prescriptions that allow for you to just kind of skim off the top 5 millimeters of duff every time you do it is another way, but that's maybe a little bit too fine. Fire and fire surrogate treatments may halt the process of mesification, but it's only when combined with mechanical treatment, right? So canopy reduction is critical. And we think, and this is totally in line with what Jonathan said earlier, probably without having read Melanie's paper, I don't know, but more active management is probably going to be the ticket, right? We're going to have to do some selective thinning, including not just the understory shrubs, but also some of the overstory trees that we don't want, and maybe even some herbicide spraying and things like that. But fire is inevitable, so we got to get busy because we got a lot of acres that need to be treated. I think that's it. Oops. Yeah, so thanks to fire, the Joint Fire Science Program, who's funded all this through and through. Could not be possible without North Carolina Wildlife. I mean, just, great partners for a quarter of a century now. And all those people, of course. Greg Chapman, I thought was going to be here. He collected about 90% of those data points. And USDA is an equal opportunity provider, employer, and lender. I'm obligated to say that.